Yes, now you can start.
Okay. Yeah. Good afternoon, everyone. This is Ambuj Kumar Jha, a PhD student at CAOS and also working as a scientist in radar group of IITM Pune. I am going to present on spatio-temporal characteristics of precipitating clouds and rainfall over the Western Ghats. Most of the content I will be sharing is a part of my PhD research, and I think some of you have already attended my thesis colloquium, which was held recently at CAOS. So some parts will be repeating for you, and therefore I request for your patience for any repetition. This work is being guided by Professor G.S. Bhatt and Dr. M.C.R. Kalapureddy from IITM Pune. Now, the topography of the Western Ghats is shown here. And here we can notice, as we know, the Western Ghats is a chain of narrow mountains that run along the west coast of India. And one notable thing about the Western Ghats is that the terrain is quite steep and complex. Just to give an idea of the complex topography of the Western Ghats, a cross section of the elevation profile along 18° north is shown here, and where we can notice a steep rise in elevation. There is almost 1 kilometer rise in elevation in just 5 kilometer of horizontal distance, which is actually quite remarkable. Another notable thing about Western Ghats is that it is one of the heaviest rainfall receiving regions in the tropics, and therefore it forms as an ideal test bed for cloud and precipitation studies. And most of the rainfall which is occurring over here is mainly attributed to the forced ascent of moisture laden monsoon winds that cross the mountains, commonly referred to as orographic rainfall. However, the spatial distribution of rainfall over this region at high resolution is not available, as most of the area is forest covered and therefore not accessible. Rain gauge coverage of the region is sparse. And therefore, only satellite based observations and model simulations are available over this region. One key question that concerns this region is that where is the location of rainfall maxima relative to the Western Ghats mountains. Most of the earlier studies have addressed the spatial distribution of rainfall based on coarser resolution satellite data and model analysis. Earlier studies based on infrared and passive microwave data, they observed the rainfall maxima offshore, whereas high resolution studies based on TRMM 2825 product at 5 kilometer resolution and model simulations, they showed rainfall maxima on the upslope of the Western Ghats. Now, this slide shows JJS rainfall climatology of the Western Ghats based on three different rainfall products. First is CMORPH at 25 kilometer resolution, second is iMerge at 10 kilometer resolution, and third is TRMM-PR 2825 data product at 5 kilometer resolution, which is the highest available resolution over this region. So first thing we can note is that the spatial distribution as well as total rainfall amount, it differ widely among different rainfall products. Second thing we can note is that the location of rainfall maxima is becomes clear with the data resolution and is actually product dependent. And for example, we can see that in case of first two figures, CMORPH and GPM iMerge, the rainfall maxima appear to be located in the offshore region or along the coastline and is not clear. CMORPH is actually based on passive microwave sensors, and iMerge is based on merged. iMerge is actually a merged product based on passive microwave, infrared, and radar calibrated estimates and later gauge adjusted estimates. Whereas this TRMM PR 2825 data is radar only product, and which gives a very high resolution rainfall information, and it is able to provide comparatively clear rainfall pattern. This product actually reveals rainfall maxima occurring over the Western Ghats. So this basically the key message I want to convey is that over this region, radar uh, product, which is an active sensor product, is actually required to understand the true nature of rainfall distribution. Therefore, we want to look closely at this particular product. So, in this regard, so we see that the spatial the left figure we see that the rainfall there is high rainfall band located along the Western Ghats, and rainfall starts to increase over from the coast, peaks somewhere over the windward slopes, and then decreases on the lee side. Note that the high rainfall band is not uniform along the Ghats, but there are heavy rainfall pockets, for example, around 14° north. But one point is pretty clear, that there is a significant influence of orography of the Western Ghats on rainfall distribution. So next, it is important to understand which orographic factor has most dominating influence, whether it is elevation of the mountain or its slope. Therefore, we first plotted the locations of peak rainfall and peak elevation across the region. Black dots are peak elevation, and blue dots are maximum rainfall locations. And it seems that there is a general correlation among between the peak rainfall and peak elevation, but the peak rainfall does not consistently coincide with the absolute highest elevations. In fact, there is noticeable offset between the peak rainfall and peak elevation, particularly at high rainfall locations around, say for example, around 14° north. Another key observation is that in the southern part of the Western Ghats, where peak rainfall locations are located over the adjacent ocean rather than over the land, it appears that the influence of orography is less here compared to other regions. And in fact, the highest peak Anaimudi is located here. And this region is known to have isolated kind of mountains, and in fact, and the mountain ranges are not continuous and wide enough. So this may be one of the reason why there is the influence of orography is less over this region. Now we also looked into special locations of maximum slope and maximum rainfall, and we find that in case of this maximum slope and maximum rainfall, there is a tighter clustering and alignment between the two compared to the earlier case. So this actually provides a very compelling evidence that slope that the rainfall over the Western Ghats is dominated more by the slope than by the elevation of the mountain. So yeah, so in order to illustrate this further, I took a cross section along 14° north, where the rainfall maximum is occurring over the Western Ghats, and it also shows that the rainfall is occurring just ahead of the rainfall is occurring just immediate to the maximum slope location, which is the red curve, and the rainfall maximum is before the summit. So which again emphasizes that slope is more dominating factor than elevation. So in this context, the following research gaps have been identified. We have seen that the orography of the Western Ghats is very complex, and most of the rainfall products are not able to resolve features at less than 5 km below 5 km resolution, which is a serious limitation for complex terrain region like Western Ghats. So this is one of the research gaps, and due to the absence of high resolution data, exact location of rainfall maxima is unknown over this region. Additionally, this vertical structure of precipitating clouds across the Western Ghats have not been well documented. Further, there is limited understanding of orographic dynamics interactions, and insufficient model sensitivity studies have been conducted to understand the orographic dynamics interactions and orographic rainfall. Now, to understand these aspects clearly, to explore these aspects at a finer scale, Uh, we used data of an X-band radar installed by IITM Pune at a remote hilly location, Mandardev, in the Western Ghats. Topography within the radar domain is shown here. This red circle shows the 100-kilometer range of X-band radar. Two observational sites are shown here, MDV and HACPL. MDV, that is Mandardev, is the radar site where X-band radar is installed, and HACPL is a high altitude cloud physics laboratory which has excellent facility of instruments to for cloud aerosol and precipitation observations, and which complement radar observations. And this dashed line passing through HACPL is actually the line of RHI scan, which is range height indicator scan of the radar. And the elevation profile along this dashed line is shown here, where the locations of HACPL and MDV are marked. The picture of the radar site is shown, where both radars, X-band and K-band, along with other instruments, are also shown. Now, I feel that there may be some many people belonging to non-radar field. Therefore, I want to illustrate a few basic things about radar. The most common types of radar scans are plan position indicator (PPI) and RHI. So, in PPI scan, the radar antenna, as you see in the animation here, is rotates 360 degrees at a constant elevation, and multiple PPI scans at increasing elevation angles stacked together, it forms a volume scan. So this volume scan provides three-dimensional structure of the clouds and storms around the radar. And in case of this X-band radar used in this study, the volume scan comprises of 18 PPI scans from 0.5 degree to 90 degree elevation. And we see that a sample PPI plot taken by the X-band radar of Mandardev at this date and time at 1.5 degree elevation is shown here to illustrate this. In another type of scan, which is RHI, which is range height indicator, it provides two-dimensional vertical structure of the atmosphere. So in this type of scan, the radar antenna is not rotating, but it is tilting upwards from near the surface to zenith. And in that process, it provides a vertical structure of clouds and storms in the radar range. These are two sample images of RHI scan. The first one is showing deep convective clouds crossing just reaching near the tropopause level, and the second one is stratiform cloud in the radar scan. Now some details on radar data processing used for this study. The radar scan strategy, as I mentioned, it consists of volume scan and range height indicator sweeps, and in this case it is repeated every 12 minutes. The volume scan of the we have used volume data of 2018 for this work, and the most important product of radar is known as equivalent radar reflectivity factor Z, which is given by this equation. So basically, a radar sends out microwave pulses into the atmosphere, which is when these pulses encounter hydrometeors such as raindrops, hail, snowflakes. Some energy is scattered in all directions, and some portion of the energy is scattered back towards the radar, which is known as backscattered power. So this reflectivity Z is actually a measure of the returned power, and it is given by this equation. As we can see here, Z is a function of number concentration of raindrops and drop diameter. And basically Z is sixth moment of drop size and is expressed in dBz units uh, due to its scale of variation. And we also know that rainfall rate R is proportional to drop size, and in fact R is proportional to D to the power 3.67, as both Z and R depend on integrals over ND. Therefore, they are not linearly related, but they are empirically related through power law fit, known as ZR relationships, expressed as Z is equal to A into R to the power B, where A and B are coefficients which depend on the nature of DSD, and they vary with the type of cloud. So for stratiform cloud, A and B will be different, and for convective cloud, A and B set will be different. Even within a rain spell, even within one rain spell, there will be multiple ZR relationships. Now, the methodology we used to process radar Z. Radar Z is actually collected in polar coordinates, and it is corrected for various things like clutter and rain attenuation. We also did bias correction because during the analysis we found that there is a significant bias in radar Z, which due to which the rain estimation obtained from ZR relationships were not accurate. Therefore, we corrected Z for bias and then used the bias corrected Z for estimating rain rate over the radar domain. Details of those corrections I'm not providing here due to the considering the time limit. Now the volume scan data obtained in polar coordinates are converted to 3D Cartesian coordinates, and the gridded volume data is having a resolution of 1 kilometer and a vertical resolution of 0.25 kilometer. The horizontal range is 100 kilometer, while the vertical range is considered up to 20 kilometer above mean sea level. And having done this, we then estimated rain rate R using various cloud type dependent ZR relationships provided for this region by Das et al. 2017. So they categorized the cloud types occurring over Mahabaleshwar region into 4 different types: shallow convective, convective, stratiform, mixed convective, mixed stratiform convective, and they gave these 4 different types of relationships. So we used these 4 different ZR relationships, and we estimated R at each grid point, and we took radar reflectivity Z at 1.5 kilometer above ground level for R estimation. So we took care to remove R less than 0.1 mm per hour from the data to considering as noise. Now, just to give a feel of the magnitude of bias correction which we implemented in our work, so this shows uncorrected rainfall estimated for the month of July 2018, and this is the corrected. This is the rainfall estimate from radar after applying bias correction. So we see that there is almost a threefold increase in total accumulated rainfall. And in fact, when we compared the radar estimates with IMD rain gauges measurements, we at these locations marked by solid white circles, we found that there is a very close agreement, almost within plus minus 7%. So which showed that the radar estimates are correct. Now, yeah. So I have already shown earlier the TRMM radar based rainfall climatology. Now to understand the finer details of the rainfall distribution, so we obtained the rainfall parameters using radar data. First is rain amount, second is rain frequency, and the third is rain rate. We see here various curves. So first is this is coastline. This thick black line is actually the summit of the mountain, and this thin gray curve is actually the represents 500-meter elevation level contour, and these range rings are actually drawn at 25-kilometer resolution from the radar. And these blank sectors, as you see, is due to ground clutter. So here also we see that the windward slopes is receiving copious rainfall, but the lee side is scanty, as which goes well with our understanding of windward to leeward contrast in case of Western Ghats. And we see that the rainfall peaks before the summit and close to 500-meter contour line, and maximum rainfall and this rainfall peak rainfall values are not actually consistent throughout this contour, but there are some heavy rainfall pockets, particularly in the southern sector. So this region receives maximum rainfall and is referred to as RA maximum zone, RMZ. Similar to rain amount, rain frequency also shows higher values along this 500-meter contour and before the summit. In contrast to rain amount and rain frequency, we observe that rain rate shows higher values along the coast and in the lee side. However, uh, the rain frequency values in the near the coast and in the lee side are less, and therefore the total rain amount is less. But in case of RMZ, the we see that the actually RMZ rainfall is contributed by both rain frequency and rain rate, but the uh, dominance of rain frequency is higher. So it is due to the significant contribution of rain frequency. The total accumulated rainfall over RMZ is high. Now we wanted to understand what are the factors which have contributed to this maximum rainfall over this location. So, actually, there are mainly two factors. Rainfall over Western Ghats is mainly modulated by two factors, which first is orographic lifting and second is diurnal heating. However, here I just first I want to give a comparison of radar rainfall with IMERGE rainfall. So you see here, the IMERGE rainfall is available at 10-kilometer resolution, while the radar rainfall at 1 kilometer resolution. And IMERGE is clearly not able to capture correctly the rainfall distribution compared to radar, and it is also severely underestimating rainfall. Even I have maintained different color scales just to highlight this difference. We see that the rainfall is severely underestimated by IMERGE, and the distribution is also not correctly captured. In fact, satellite estimates studies which have been done for IMERGE data have shown that the satellite estimates based on IMERGE has a difficulty in capturing the true nature of rainfall distribution and magnitude where rainfall is contributed due to orographic lifting. So earlier studies have shown this, and this bias is I have calculated at 10-kilometer resolution, which is basically IMERGE minus radar estimate, just to highlight the difference between just to give a feel of the magnitude of the difference. We see that over rain maxima zone, almost up to minus 5,000 rainfall is being underestimated by IMERGE. Whereas in case of lee side, there is some overestimation. But however, this is a major concern that the orographic lifting mechanism, the algorithm is not able to capture the rainfall contributed due to the orographic lifting, and which is why it is not able to produce a correct magnitude of rainfall over this region. Now, yeah, this slide I will come back if time permits. Yeah. Now, just to give a feel of the the occurrence of different types of clouds occurring over the Western Ghats. So this animation is maximum reflectivity product of radar created for 25 June 2018. So we see here, so starting from the day to the end of the day, we can see here. So as the name suggests, this is the maximum reflectivity plot, and this plot basically helps us visualize where the strongest reflectivity values occur, both horizontally and vertically. This main plot is the top to down view, while these side plots are vertical cross sections along east west and north south direction. Basically, if we yeah. So if we see, we can see initially during nocturnal hours, there is clouds are generally seen over the coast, and they are moving from coast to windward slopes. Uh, and one notable thing is that the clouds are deeper over coast, compared to inland areas. You see there is a slope kind of structure here, and we also see there are some scattered storms which develop and organize and produce heavy rainfall. With the progress of the day, high frequency of storms are seen over the elevated slopes, and they are moving to lee side. So this clearly shows that diurnal heating is important, and it aids orographic lifting. So there is this is an active convection day and active rainfall day, and clouds are occurring almost throughout the day. Uh, yeah. So now this is again a uh, along this cross section, the RHI profile which I mentioned earlier, the RHI scan images for the entire day of 25 June 2018 are shown here. Here again we can observe similar pattern where deep convective clouds occurring over ocean. They form over ocean and low-lying slopes, and they move towards windward slopes. And we can see the top height of the clouds. It decreases. Clouds become shallower as they move inward towards. They rise over windward slopes. So this again highlights the same thing, but at higher resolution. Yeah, so one question we wanted to answer: what type of clouds prevail over this region? So we see that basically shallow clouds are dominant over the RMZ, and deep clouds are mainly dominant over lee side and the coastal sides. And therefore, major proportion of rainfall amount over RMZ is contributed by shallow clouds. Now coming to diurnal forcing, we see that there is a strong diurnal heating occurring. Uh, so shown during 15 to 18 hours, and a maxima is seen. This cloud top height indicated by 18 dBz ETH is also showing a slight increase in cloud vertical extent during daytime. Again, the 10-meter winds from era 5, they also show that winds become stronger during daytime. So this deepening of boundary layer height is also seen during afternoon hours from 12:30 to 18:30, and which facilitates low Brunt Brashala frequency and higher Froude number, which leads to enhanced cloud-based mass flux and increased rain amount, uh, causing higher rainfall accumulation over RMZ. Yeah, now I will go to the this orographic factors. So as shown earlier with TRMM product, again we repeat the exercise here for the radar domain to understand the finer details, and we see here the that the RA maxima shown by this blue dots, and slope maxima shown by this red dots. So these appear to be closely tied then to local maximum and then to local mountain peak, particularly in heavy rainfall areas, example RMZ. uh, Both the blue and red dots can be seen to be closely aligned, whereas for low rainfall areas in the northern sector of the radar, where low rainfall accumulation regions were located, so there is an offset of about 5 to 10 kilometers. So uh, so this means that slope is the dominating factor. However, we have seen that not all steep slope locations receive heavy rainfall, and vice versa. So this implies that slope alone is not sufficient. So there is an additional controlling factor which is causing the accumulation of rainfall over this RMZ. So then we looked into wind direction. So basically, wind direction in most of the earlier studies, the wind direction has not been considered for understanding the rainfall, spatial distribution of rainfall. So here, when we looked into the wind direction, we find that in the northern sector of the radar, where low rainfall regions are located, the winds are aligned along the orography. If you see closely, while in the southern sector over RMZ and other locations where heavy rainfall was present, heavy rainfall accumulation was there, the winds are more perpendicular to the orography. So more perpendicular winds imply that there will be higher degree of forced ascent, which may lead to heavy accumulation of rainfall. So according to linear model for orographic precipitation, the vertical velocity or rainfall is directly proportional to U naught sine alpha into del H by del X, where U naught is the background wind speed, alpha is the angle between wind and local terrain, and del H by del X is mountain slope. As you can see here, if this is the direction of the winds striking the mountain. The mountain orography is oriented in this direction and the wind is striking at an angle alpha. So higher the alpha means if the alpha is close to 90 degree, there will be higher degree of forced ascent, and it may lead to heavier, stronger updrafts, and it may lead to heavy rainfall over this region. So for the RMZ and other heavy rainfall locations, we formed a hypothesis that enhanced rain amount is due to steep slopes plus larger alpha. So to understand this in detail, we conducted WRF experiments. This paper on this hypothesis and the spatial distribution of radar-based rainfall at 1 kilometer resolution is published in monthly weather review recently and is available online. So I request you may kindly go through that. Now coming to WRF simulations and sensitivity experiments. So our objective is to understand that whether the slope and the angle are really contributing to the observed rainfall distribution. So first thing, so we carried out 3 experiments. In the first experiment, we found out the best suitable of physical schemes. Means which combination of microphysics scheme, planetary boundary layer scheme, and surface flux scheme will work for this particular region and for this thing. So which will give simulations closer to observations. So we found that so having done that, we then conducted 2 experiments. In first experiment, we uh, smoothed the terrain, and in the second experiment we rotated the terrain. So in this experiment, the smoothing terrain experiment, we understood the role of slope, and in the second experiment we try to understand the role of alpha, the angle between wind vector and mountain orientation. For this, we set up the WRF model. We made a nested WRF model configuration of 3 domains. The first domain is 27 kilometer resolution, the middle one is 9 kilometer, and the third one is innermost is 3 kilometer resolution. We took an active rainfall period during 13 to 17 July 2018, and we after discarding initial 18-hour data as a spin up, we took 14 to 17 July 2018 for our analysis. And we found after several combination of schemes, we found that WSM6 is MYNN 2.5 and revised MM5 surface layer scheme. So these are working best as this combination of scheme showed good agreement with observations. Now, this slide compares radar observation with respect to WRF simulations during this simulation period, that is 14 to 17 July 2018. So we find that the rainfall pattern is actually captured well by WRF. So WRF is also showing higher rainfall ahead of the summit and immediate to the 500-meter contour in agreement with the radar observations. However, there is a very underestimation of rainfall, particularly over RMZ. In fact, WRF is showing rainfall maximum along this 18-degree north latitude, so which is actually the highest slope location. So it may suggest that WRF is able to capture the slope effect but not the angle effect of the winds. So WRF is also able to show similar pattern of slope and maximum slope and maximum RA, and we find that maximum rain accumulation locations are also occurring immediate to the maximum slope location, similar to what we observe. Yeah, so we compared WRF simulations with ERA 5, and we also compared WRF profiles with reduced onto profiles over HACPL, and we found that they are in agreement, uh, not largely, but yes, they have a quite agreement. Uh, and then we calculated vertically integrated moisture flux convergence by integrating moisture flux convergences from surface up to 300 hectopascal, and we found strong moisture convergence values along this 500-meter contour, and the highest values are located around 18 degree north, where maximum rainfall was occurring in WRF simulation, and this actually indicates that there is a strong orographic lifting might be occurring. So we calculated orographic lift using this equation, which is actually the dot product of horizontal velocity and the terrain vector, the gradient of terrain height. So in the orographic lift also we found that the maximum is occurring, the orographic lift maximum is occurring at the same location where the rainfall maximum is present. So this implies that a strong orographic lift is responsible for rainfall distribution. However, WRF is not able to show very highest values over RMZ. Uh, so uh, Basically, it infers the slope as the main dominating factor and is not able to account the wind angle alpha effect into the things. Now, in this experiment, terrain smoothing experiment, so we used a Gaussian filter, uh, which is given by this equation, and we varied sigma values to smooth the terrain. So at sigma is equal to 1, 2, and 3, the slope of the innermost domain is reduced by around 30%, 50%, and 60%. So which can be seen in this figure. So the blue curve is the control original orography, and the as we increase the sigma values, so we can see the how the elevation profile is getting smoothed, and now this is showing slope variation across this 18-degree north. So we see the blue curve again is the control slope variation across 18-degree north, and with increasing sigma values we can see how the slope is getting reduced. So this is just to give an idea of the slope variation being taken, and we found that with increasing smoothing of the terrain, the rainfall is decreasing further and further, particularly over this 18-degree north, where the rainfall maximum is located. We see that with respect to control, which is shown by this blue curve, the rainfall is decreasing by 25%, 45%, and 55% for sigma is equal to 1, 2, and 3 values. As you see here, how with increasing smoothing, the rainfall values are decreasing. Again, the winds, however, with increase in smoothing of terrain, lower level winds they are becoming stronger, and lower level winds they approach with higher speed, and but they slow down along higher elevations. So these variations are noted here. Next, we also looked into the cross section of vertical velocity along with water vapor mixing ratio along 18-degree north, and we found that there is a in the original case we see a strong updraft present along 18, along at higher elevation, so which is getting reduced in terms of strength and height as the slope becomes smoother. So and also the vertically integrated moisture convergence flux also gets weaker and weaker with respect to control. The orographic lift is also showing decrease in values with respect to control. So this all indicates that when there is a smoothing of terrain, the orographic lift decreases, due to which the rainfall is decreased. Now we rotated terrain slightly to modify incident angle of winds, and this is just one sample case. This is the original terrain, and in this case, we have rotated the terrain by 5 degree clockwise, very slightly, and we found that with respect to, in the original case, the rainfall maxima is located along 18 degree north at this location. However, when we rotated the terrain, the rainfall maxima is shifted here. So, which was earlier, uh, here it was present but not so prominent, but here the rainfall has decreased and the maxima is now located here. So this implies that with the change in wind direction, the rainfall is decreasing. So again, the orographic lift also shows decrease with rotation of terrain. So which is the basic reason for the decrease in rainfall over the. Uh, so we draw following conclusions in this context. That the highest rain amount and frequency occur ahead of the Western Ghats summit, and rain rate peaks over the coastal and lee regions. Rain amount maximum is closely tied to the local slope maximum than local summit. High rain amount over RMZ is contributed by both rain frequency and rain rate. However, rain frequency is the dominant contributor. Strong westerlies blowing more perpendicular to the orography during afternoon, they facilitate greater upslope flow, leading to enhanced rainfall over RMZ. And WRF ARW experiments also support this hypothesis. It shows reduced rainfall with smoothed or rotated terrain, which is associated with weakened orographic lift. Now, at the end, I just want to give a glimpse of X-band radar at Mahabaleshwar, which is in setup stage now at Mahabaleshwar. Uh, the topography map is shown here, and this is the coverage of the X-band radar being set up at Mahabaleshwar. So this is 100 kilometer range of the radar. So this is a new SSPA based radar which is currently being installed here, centered at HSCPL. So this is the HSCPL lab, where at the terrace you can find facility of instruments. Near to this lab, a radar tower is constructed, and on that tower top, the radar is installed and will be operated. You see here a picture from the initial days when the foundation of the radar tower is being dug, and the radar, after the foundation is done, the radar tower is being constructed on that. And this is the installation of the radar, uh, pictures from installation of the radar. So this shows the radar pedestal being mounted on the tower top. This is during the installation, when the installation of the radar antenna was in process. This is when radome installation was ongoing, and finally the radome and the radar system is installed over the radar tower. And this picture is from in March. There was one GB meeting in Mahabaleshwar, and some of the GB members, along with Secretary, Ministry of Earth Sciences, our former director, and my former project director, along with Bhatt sir and Surya sir and many other people, guests, Joint Secretary of Earth Sciences, they all came to visit the radar site and to HSCPL lab. So this picture was taken, and this picture is of our my teammates, and he is Dr. Kaustav Chakravarti, who is in charge of this X-band radar, and he is Hari Krishna Devisetti, and we all are working on this radar project. So this picture was taken during our radar training in Vaisala factory in Finland. So in the background there is X-band radar showing up. So with this, I would like to thank you for your kind time and patience. Yeah, thank you all.
Thanks, Ambuj. Any
Yeah.
questions? Okay, if there are no questions, then sir, you can just.
Okay, I will stop sharing.
Yeah, sure.
Amber, I want to ask you, I didn't see a comparison of the diurnal cycle of rainfall between iMerge and radar. You must have done it, right?
Sir, can you repeat? Sorry, I could
Yeah.
not hear you properly. Yeah.
Yeah. You must have compared the diurnal cycle of rainfall between iMerge and radar.
No, I have just compared the accumulated rainfall.
Not the diurnal cycle.
No, diurnal cycle I have not done. I have not
I
done
think it's
yet.
worth doing because iMerge is putting out data on an hourly basis and are wondering whether it's real or unreal. So since you have the data, make a short presentation on that to show how good is the, for that data,
Okay.
how is iMerge comparing with your data, okay?
Okay. Okay. Sure,
Thank you.
sir. That I will do. Yeah.
Yeah. Okay, let's get back to the state of the monsoon. As of yesterday, the latest data is not yet available. As of yesterday, you see that you are 15% above normal, cumulative. And what's interesting is clear distinction between northwest, central, east, and south. So it's a clear, these two regions are getting above normal and these two are getting below normal. And what's interesting is the first 9 days, every 8 days, even the ninth day, we are almost 30% above normal in the first week. I don't think they'll continue, we'll see. It will come down, but it is quite impressive. Okay. Then I was curious to know how good the forecast of daily rainfall, which I normally don't discuss. So this was the actual rainfall till 8:30 this morning. Okay, there was a nice peak in Madhya Pradesh of the order of 70 millimeters of rainfall. Okay, this is the climatology. You can look at that. This I want to compare with forecast 2 day ahead by both GFS and by European Central. And I'm quite impressed. It's very close to the observation, and both are very similar. Both have one thing, one branch here. And depending on how much everything you do, you get somewhere around 65 or so. Now, of course, there are peaks of the order of 80 or 100, but I'm quite sure that the density of rain region is not that high to pick a peak. That's always a problem with ground data. But I'm quite impressed that both major forecast centers are reproducing 2 day. That means 2 day forecast is very good. Okay. Now, this you must remember, maybe next time we'll talk about the catastrophe in Texas. See, 2 day forecast of rainfall are good. They're not perfect. There are errors in high rainfall. But in Texas, it's amazing the local people, local leaders ignored that. Okay? So you had more than 100 deaths, probably much more. So to me, this is something which is surprising that when the National Weather Service announced heavy rainfall, they didn't evacuate people from the river bank. It's absolutely surprising. So this is something we also have to learn, that sometimes people ignore warnings because sometimes they give warning which doesn't come out true. It's like shouting about tiger and tiger doesn't come, and next time you forget it. So this is the issue. Okay. So if you look at the subdivisional average, I would say that except for two subdivisions in South India, and of course the Bihar region and northwest are the ones, northeast are the ones which are still below normal. So we are running at 15% above normal, which is very good. And you look at the time series, to me it's very impressive that from 15 June onwards, except for 2 days, it has been always been above normal, and it may continue for some more time. If you look at only the core monsoon zone, it's even better. Core monsoon zone goes from 15 June till today, this 9th. Okay, so to me that is an unbelievably long active monsoon season in the core zone, which is a very good sign. This is covering the 4 regions, again clearly showing that northeast and south are the ones which are doing not well compared to these two. And let's look at the All India forecast. This is for the last week, and I would say not so good because we saw that couple of days forecast was very low, and so was here. So I would say not that good, but this week I would say they are better in terms of forecast. And not only that, more than the forecast, I think we should look at this tendency. And that is very good. They are correctly predicting the tendency for the rainfall increase, and you will see that it will start going down. Okay? So already first day, and today also somewhere here. So it correctly predicts increase and decrease, which is a good sign for the model. Okay? So it got the rainfall above climatology all the way correctly, and got the trend increasing and decreasing trend very correct. So that's all a good sign. And this is the forecast for the coming week, and you already see that there's a clear indication of decrease. To me, this is not surprising. To have more than 3 weeks of active monsoon cannot sustain because it got energy to run the monsoon. At some point, the energy is not there, so it will decline. There's no surprise. But that it continued till 8th or 9th July and then went down is very interesting. And let's look at the spatial pattern till yesterday that was predicted by the two, that is ECMWF and GFS. The big difference was over Pakistan. Okay, big difference. So let's see what is the actual data. Actual data is this. Okay, slightly different date. I'm not looking at the exact 8th July, but clearly ECMWF has done better. This observation, okay, which must be satellite viewing. So to me, ECMWF is doing usually better than GFS over Pakistan. And if you look at South India also, let's go back to South India. Yeah, South India, both of them got it right. Although if you compare the two, and I think the color bar is same. Yeah, so I think maybe GFS was slightly better. If you look at GFS, it is well below normal, and so is this. Yeah, so GFS does slightly better in South India. Now, sometimes anomalies can be misleading. So better the actual value. This is weekly rainfall up to yesterday, predicted by GFS and ECMWF. The key difference I wanted to see is, of course, this part and this maximum. So GFS predicted up to for this period of 7 days, 7 days, value close to 150, 200, while ECMWF is slightly lower. So this later on was comparing with traditional data to say how good it is. And this is the anomaly for the coming week now, that is after tomorrow. And again, I find it interesting that ECMWF shows more rainfall than this. I don't know why. It's very interesting that systematically ECMWF shows more rainfall than GFS over Pakistan. Now, this is the forecast from IMD. This is for the last week. I think which came out more or less right. These peaks are correctly reproduced. and this is the forecast for next week. And clearly you are seeing last week it was all India was 31% above normal weekly rainfall. Coming week is minus 10%. Okay, so it's definitely weakening. That's very clear sign. Now let's look at the forecast from ECMWF website, and I find it interesting because there is a spatial scale. This is remarkable. I'm not saying this. You see it now and then. This is a very large scale feature, not local. And so is the below normal rainfall. So this is the pattern, ground pattern. And you do see it from time to time during the season, but I'm not seeing anybody do a proper UF analysis to see how often does it occur. Okay, if any of you have seen it, you let me know. If you just take the Asian monsoon or a single region, that's debatable, but you can try it out and ask yourself based on either, I would say only thing you will have is for the past 20 years will be IMERGE. If you want to go longer, you can look at some of the GPCP and so on. Ask yourself how many times this dipole pattern, which spatially extends all the way beyond Japan, very, very long scale. And it's worth asking what physical phenomena, what wave or what pattern will give you this phenomenon. And this is continuing for the next 1 week. This, let me remind you, this was 40, this 42 July, same thing I looked at today. That means a more recent forecast, slight changes occurred. You can see that this continuity is somewhat lost, it also lost, but there's still the pattern is there. Although it was much more continuous in the previous forecast than the current forecast. So that, and this I think is new, let me see. This lower part I think is not there. So it was there, yeah. I think it was there in both of them. Slight changes are occurring day to day. Now this is the next week, 21st to 28th July. Again, I'm impressed by this huge thing, okay? Pattern extending all the way to Japan. So proceeding for at least 2 weeks, okay? And this is the forecast of the week after that, and you see that disappears. This thing is, but this is persistent. This what you might call the weak condition is from all over India across the world all the way there. So that also is worth asking, what is that causing that pattern? Now I'll end this by a little thing on illusion. So all of us use all these nice color bars and show this one, but you must remember that if you show the same picture to two different people, they will not agree because your eye sometimes cheats you. Okay, so how many of you can see a circle here? Put your hand up. Anybody can see a circle? Anyone? Yeah, okay. So you have a different perception. So I will now highlight it, all of you will see it. Okay. So this is the problem with eye. When you want to see patterns, sometimes you're influenced by your previous knowledge or the way your eye processes the information. So you have to keep this in mind when you make plots and so on, because sometimes when you see a paper and the guy says, he sees some pattern, I don't see it. That's because he didn't quite do it. So remember that when you are making plots, you have to make sure they're not you, but the others also are able to see that. Okay? So it's a very good example. If you go to internet search, there are about 30 or 40 different illusions that have been discussed by psychologists. Because today with more research on brain, people are trying to understand how the brain processes this information. Some people see circles more quickly, others don't. Okay, but once you point it out, of course, your brain will immediately reprocess your data. Okay, thank you. So next week will be Raviraj Shinde, right? Yeah.